This is a lesson in collisions in the momentum unit. In a previous lesson, I had introduced momentum, total momentum, and impulse. How impulse, a force applied for a certain amount of time, can cause a change in motion. In a lesson after that, conservation of momentum, I talked about how if that external force, if that's zero, that results in no change in momentum, and we get the conservation of momentum concept coming out of that. And remember, you have to check, is the external force equal to zero prior to applying conservation of momentum. So this allows us conservation of momentum, and I don't know if you've noticed so far, but allows us to deal with interacting objects when they interact in complex ways, right? Two objects that smash together and there's a bunch of forces going on, there's sound, there's heat, there's lots of things. But the simple quantity, mass times velocity, if we use that and a conservation of it, we can figure out things about the system before and after that event. We're not interested in the details of what happens within it, only before and after. So when we look at collisions, and as I just mentioned, in collisions, there's complex things going on. There's a sound created. There's often some friction between the objects. It may cause some deformation or heat to be created. And so there's energy going on. There's energy transfer. You might notice that. And this brings us to the different types of collisions. A differentiating factor for different types of collisions is the energy remaining the same during them. Okay, so in an elastic collision, the total kinetic energy of the system remains constant. And that means there's no energy lost to things like sound, heat, deformation. All of the energy that was there to begin with retained afterwards. So the inelastic is when total kinetic energy decreases in some way. You have some sort of sound or some deformation or some heat loss, right? That there's energy being moved, transferred out of the system somehow, and that results in a loss in kinetic energy, right? There's no potential. It's not relevant. There's things moving before, things moving after, and so we look at the kinetic energy. And so we can quantify this. Kinetic energy final minus kinetic energy initial. We can calculate that. And that is the defining characteristic between two types of collisions. Something I see students have a misconception about when it comes to this concept. This deals with energy only, but for some reason students get into their head that inelastic means that they stick together, and elastic means that they don't stick together. And that's my warning, is that inelastic collisions can happen and those two objects not stick together. This is the majority of collisions. If you think about two cars crashing, they don't always stick together afterwards. But there's definitely a sound, and there's definitely deformation, and there's definitely friction and heat between those two surfaces. So for inelastic, I will write this down. Does not necessarily mean they stick together. And with an exclamation mark. One final thing I put on this slide before we move forward to examples is to note that I have a relationship between kinetic energy and momentum. If I think of kinetic energy as 1/2 mv squared, if I plug in what I know about momentum, P equals mv. So if I solve that for v, I get P over m, and I can plug that in where I have v here and square it. When I simplify, I have an m on top and two m's on the bottom. I end up getting P squared over 2m. And I will put this on your equation sheet. I don't know if your teacher, if you're not my student, what your teacher does, but this is such a useful equation, because if I'm looking at conservation of energy and conservation of momentum, I can relate those two directly rather than having to introduce a velocity term in between. And you'll see how that will work out in the next couple of examples. The first example I chose is a 1D problem. This is a 1D problem. The dart of mass 10 grams it looks like, is fired at and sticks to a block of 85 grams. That is initially at rest on an initial horizontal surface. Okay, so I'm encoding sort of the initial situation. There's a 85 gram block here. Here's the second block. I'll call this M2. The dart is flying at it. Here's a dart, and it has M1, and it also has some V1 initial. The final speed of the two together. So I don't know this V1 initial. This V2 initial equals 0. So that's sort of the initial information that I've given in the problem. I'm going to assign a coordinate system. So we have a positive for the direction of the vectors. And we'll put a final in here. Afterwards, it says the final speed of the two together. So they stick together. Here they are. I'll put that in there. And there's some V final, and I can put down here like I did before, M1 plus M2, they're stuck together. Okay, so this is looking familiar. I might be inclined to find that initial speed of the dart because it's an unknown. But let's look at what we're asked in the problem. It says, how much kinetic energy was lost in the collision? Okay, so the change in the kinetic energy, or we're going to do the kinetic energy lost. The kinetic energy lost will be the initial kinetic energy minus the final kinetic energy, right? The initial kinetic energy is going to be a larger number, so then when I calculate this, it will be a positive value. Of course, the change in kinetic energy, it's the opposite this. Final minus initial, it would be negative. But we're calculating the kinetic energy lost. So you may knee-jerk, and because of your experiences with energy, you may put in here 1/2 mv final squared and 1/2 v initial squared, etc. But we are going to use this relationship, kinetic energy equals p squared over 2m. You'll see the elegance of this in a second. The initial kinetic energy then is going to be p squared over 2m, p initial squared. I don't know that value, but I can put it there. And then I'm going to subtract off p final squared over 2m final, and this will be an m initial. We check that there's no external forces applied on the system. The dart just hits the block. That's it. This is before they have a chance to move, so it's just like a picture in time. There's no external forces on it in that time. And also, so that lets us say that the initial momentum equals the final momentum. And if you're keeping track of the algebra here, I just solved this problem. Like, what's the initial momentum? If I don't know the initial velocity, how do I find the initial momentum? Well, I'm going to use this identity. The initial momentum is the final momentum. So when I do this, I'll put the final momentum in where I see the initial momentum. So I have p final squared over 2m initial minus p final squared over 2m final. Remember, that's a final mass. And this doesn't equal 0 because there's different denominators here. I'm going to factor out the p final squared over 2 and show you that you have 1 m initial over 1 m final. Okay, so I know these quantities. These are actually quantities that I know. P final will be m final v final. Well, m final equals both of these added together, which is 0.01 plus 0.085. That's 0.95, 0.095 kilograms. V final, we're given 5.2. And so we have masses and the initial velocity or final momentum. So let's plug this stuff in. 0.095 times 5.2 quantity squared. That's P initial or P final. It is P initial, but that's how you calculate P final. over 2 times 1 over 0.01. The initial mass is 0.01, and minus 1 over the final mass, m1 plus m2, which is 0.095. When you run this through your calculator, you can guess that this is a non-zero value. You actually get 10.9174 joules. That's how much energy was lost. Okay, so even though the momentum stays the same, the momentum definitely stays the same, it gets transferred in different ways to the different objects in the system. And whatever happened in that collision, there was 10.9 joules lost. So there was probably a sound. There was definitely deformation, right? The dart goes into the wood. It causes some sort of deformation there. And the two surfaces were in contact, so there was some sort of friction. So that's where that energy goes. The second problem I've chosen is a two-dimensional problem. I chose this because momentum is conserved in 2 dimensions, and we can use that and how to use that in 2 dimensions, conservation of momentum in 2 dimensions. It says a 5.5 kilogram bowling ball is moving at an initial speed of 9 meters per second, and it collides with a bowling pin, which slides away at an angle of 37 degrees to the initial direction of the bowling ball with a speed of 8 meters per second. Okay, so I'm kind of getting a picture in my head here, and I'll do an initial. We're going to have the initial direction of the bowling ball, and that can be the positive x direction. And so the bowling ball was initially moving V1 initial, and we have an M1. They tell us and there's a pin here. And apparently they don't hit on head on, they hit at some angle. And so then afterwards in the final, and let me draw this axis here, plus x. In the final, afterwards, okay, the pin goes off at an angle of V2 final, which we know is 8 meters per second. They give us that. We can also say V2 final. Here's the positive y. V2 initial equals 0. It was just sitting there. The bowling ball hit it. Afterwards, the pin goes off at 37 degrees here. And I'm going to exaggerate this angle so you can see it better, but it's only 5.3, right? Calculate the magnitude of the bowling ball's final velocity if its direction is at an angle of 5.3 degrees to the initial direction of the bowling ball, but on the opposite side of the pin. Okay, so we're on the opposite side of the pin, and it's going off at 5.3 degrees, and this will be V1 final. And we don't know that value. We know this angle is 5.3 degrees. So you're getting this feel of vectors, right? When I look at the momentum or velocity vector for that pin after the collision, it has an x component and a y component, which you can calculate with trig functions. And the bowling ball has its own x component and its own y component after the collision. What I'm going to note now, before we get too far involved with calculations, is this sort of larger concept. When I look at this, we're going to assume that there's no forces, that F external equals 0. And so what we're going to get is P initial vector equals P final vector. What does that mean? Yeah, we have angles going on, right? But the initial momentum vector is just caused by M1. So there's P1. It's just caused by M1. It's in this direction. There's no components to it. What this concept is saying is that afterwards, P2, P final, right? P final, it is the same as the P initial. These two vectors are the same. And so you will see this in the vertical direction. Whatever component that pin has in the vertical direction has to be equal and opposite to the component of momentum that the bowling ball gained downward, okay? Such that this final momentum vector ends up being in the same direction with no vertical components like the initial momentum vector had. Okay, so let's do some math. Let's divide this up. So this is the strategy. We're going to take it and divide it up into two different parts. We're going to have P initial in the x direction has to equal P final in the x direction. P initial in the y direction has to equal P final in the y direction. I'm going to deal with this over here first just because I think it may be a little bit easier. Let's see. The initial in the y direction. When I look at the initial momentum in the y direction, I have 0. After the collision, I'm going to take the momentum of each of the two separate objects in the system, and I'm going to have two components. So I'm going to have this blue component upward for the pin. I'm going to have this green component downward for the bowling ball. So afterwards, I'm going to have M2V final 2 in the y direction. And then I'm going to have, and I'm just going to put a minus sign in here already because I know these two are equal and opposite. M1, V1 final in the y direction. So we're going to solve for, I'm going to set them equal to each other. And I'm going to put in some trig functions while I'm at it. The y component here, I can see it's the opposite from the 37. Same with the 5.3. The y component is the opposite. So these components will have sine of the angles in them. So I can write out M2 V2 final sine 37. It's the top one. Sine 37 equals M2 M1 V1 final sine 5.3. V2 final is a number. M1 final we're trying to find. Can I calculate it from this equation? Let's see. V1 final equals M2 V2 final sine 37 divided by M1 sine 5.3. Yeah, it looks like it. So M2 is 0.85. V final 2 is 8 sine 37. And then we're going to divide by M1, which we know is 5.5. And multiply by 5.3. When we solve this out, we get V1, M2, V1 final equals 8.047897 meters per second. You can see that we still have this over on this side. If you had other unknowns in the problem, you'd be able to solve for something down here. But we were given enough in this problem to solve. I wanted to follow up with part B. Let's go back to part B. I solved for part A. This is part A. Part B says, was the collision elastic? So, like I was mentioning, a student may say, yes, it's elastic because they don't stick together. But that's not the quality that we're looking for. What we're asking for is the kinetic energy lost equal to 0? Is it equal to 0? Okay, so we'll do kinetic energy initial minus kinetic energy final. We can take what we know, our new equation here, P squared over 2M for energy. So we have P initial squared over 2M initial over P final squared over 2M initial. P final squared over 2M final. Okay, we can plug in what we know about P initial and P final. They have to be equal to one another. Even at an angle, right? This is when I square a vector, I'll just get its magnitude. So these are the magnitude. So this M final here is both of them added together, even though they move away separately. All right. So we're going to get P final squared over 2 times 1 over m initial minus 1 over m final. I'm not going to calculate this actual value. It doesn't ask me to calculate it necessarily. All I'm going to say is that this term is not equal to 0, and so we know the kinetic energy lost is not equal to 0, and so it's not elastic. It's a non-elastic collision. So again, this is a situation where you see the two objects not sticking together, but we had a loss of energy, and that makes it inelastic. And one last time, just to go over strategy for a 2D problem, noticed I did my initial and final sketches, and I identified this initial momentum vector. Afterwards, when I have these angles, and if you have angles prior, you can divide your velocity vectors and thus your momentum vectors into the x components separate from the y components. And this strategy is similar to forces when we added velocity vectors, when we added displacement vectors. It's vector addition, and you do the x components separate from the y components. And then that gives you two different equations. If you have two unknowns, that's a good situation as well, just to highlight that strategy.